Hello everyone. Welcome to the third webinar of BioMeca. Today, I will speak about how to highlight the effects of blue light exposure in skin using atomic force microscopy. So to begin, I would like to introduce myself. I am Jean-André Lapart, and I am the new lab manager at BioMeca. During and after my PhD, I worked on cilia formation and function both in mammal and in Drosophila, and my field of expertise implies biochemistry and imaging, such as classical imaging and super resolution imaging. After 6 years in the academic field, I had the opportunity to join BioMeca since August and to begin a new adventure. So BioMeca is specialized in biophysics in life science, such as cosmetic and pharmaceutical field. Our innovation team is composed of different parts. The first one is to develop the new innovative field in order to provide new solutions. The second one is the hardware part and 3D printing to develop a new product. And then we are able to adapt our protocol and our technique to your sample to provide you some customized services. So today, during this presentation, I will introduce you what is blue light. Then we will speak briefly about AFM and what we can do with it. And we'll finish by how can blue light affect skin structure. So what is blue light? Light is composed of several waves, and to understand it, I will briefly introduce the electromagnetic spectrum. So the electromagnetic spectrum is a range of electromagnetic radiations that possess specific frequencies, wavelengths, and energies. These electromagnetic waves have wavelengths ranging from around thousands of kilometers down to atomic nucleus size. The spectrum is divided into separate bands, and these bands are called by different names. These bands begin at the low frequency end of the electromagnetic spectrum, corresponding to long wavelengths, and these bands, such as broadcast band and radio band, for example, and these bands end at the high frequency end of the electromagnetic spectrum and are associated with short wavelengths, such as X-rays, gamma rays, or cosmic waves. It is important to note that longer the wavelength is, and less the damages associated with heat are weak for human. As the opposite, shorter the wavelength is, and more the associated damages are for human. Today, we are going to focus about a specific band, which is located between the ultraviolet and the infrared band, that is the visible light band. Light is just one part of the electromagnetic spectrum, and our eyes can only detect visible light from 400 nanometers to 700 nanometers. Blue light is almost found at the end of the visible light spectrum and is associated with a short wavelength and high energy, meaning that blue light can be deleterious for humans. Blue light can be divided into 3 parts according to its effect on human. The first part of the blue light is a high energy visible light that have been shown to be involved in making important damages for human and more precisely in retina, for example. However, other studies have shown that this kind of wavelength of the blue light can be used for some treatment in case of eczema or psoriasis. The second part of the blue light is known to participate to the suppression or to a delayed production of the melatonin, which is the sleep hormone, and this can lead to an increase in alertness or an increase of heart rate. The last part of the blue light spectrum is classified as benefic blue light, as it is already used in various treatments in the case of sleep disorders or seasonal depressions. The main source of light is the sun, which contains all the colors of the visible spectrum, and this is called white light. Thus, sun is our biggest source of blue light. Because of the technological advances, we also collect blue light from other sources, such as PCs, TVs, LED lights, smartphones, and tablets, for example. As well, our consumer habits have evolved with time, and we spend more and more time every day looking at our screen, so we are more and more exposed to blue light every day. As said before, blue light can provoke many troubles in eyes and also to induce dysregulation of several physiological processes, but blue eyes can also induce some damages in skin. And these kind of damages are less known and less characterized. So today, in this presentation, I will share with you some results that we have obtained at BioMeca on the characterization of the effects of blue light exposure in skin using atomic force microscopy. So now let's move on to some generalities about the principle of the atomic force microscopy and see what we can use from AFM to study blue light effects in skin. So the principle of the AFM is as follows. As you can see on this scheme, we have a cantilever with a known spring constant on which we can apply known force, and this will allow the movement of the cantilever into the sample, and this indentation into the sample results in variations of height. And these variations of height can be recorded by a laser beam that hits the surface of the cantilever, and the laser beam is reflected on a photodiode to 4 quarters. The data that we obtain from this kind of acquisition are this kind of curve, which is a force indentation curve. As you can see of this graph, we have different stages on the curve. The first one is a flat curve corresponding to the approach stage, where the cantilever is not in contact with the sample. Then we have an exponential curve corresponding to the indentation stage of the cantilever into the sample. And then in red, you have the retract curve corresponding to the moment where the cantilever goes out from the sample. We have an important area here, which is a contact point where the cantilever enters in contact with the sample, and from this point we are able to fit a theoretical model in order to convert this curve in a quantification of the Young modulus that corresponds to the stiffness of the sample. So among the possibilities that AFM offers, we are able to analyze some lateral cross-section from a human skin sample. And for this study, we were interested in the evolution of the properties of the bioproperties of skin during aging. So we performed AFM measurement and we performed high resolutive images of force indentation mapping, and we focused on three features of the sample: the topography, the stiffness, and the adhesion force. As you can see on the first image, the topographic image, we can see both epidermis and the stratum corneum, which is composed of different layers. The second image corresponds to the stiffness of the sample, and you can see that and these images show a stiff structure, which are the corneocytes. And if we merge the first and the second images, you can see that these layers of the stratum corneum corresponds to the corneocyte. The third image shows the adhesion force that corresponds to the intercorneocytic cement as represented under the form of layers, and these layers are the area between corneocytes. The intercorneocytic cement is composed of lipid and water, and more we have lipids, more the skin barrier is able to keep water. Thanks to this analysis, we're able to study skin hydration on section during aging. And as you can see, during aging, the adhesion force decreases with time, meaning that skin hydration decreases during aging. And this is associated with an increase in corneocyte stiffness during aging compared to a young condition, meaning that we have, for example, more desquamation of the skin during aging. Of course, we can also perform AFM measurements directly on a full explant. In this study, we are still interested by the evolution of the skin stiffness during aging. And so to do that, we performed AFM measurement directly at the surface of the sample, but by indenting enough the sample to be sure to measure the impact of aging on both epidermis and dermis. Thanks to this process, as you can see on this graph, the overall stiffness of the skin decreases with age compared to more younger conditions, meaning that skin stiffness decreases with age. So with AFM, we can allow the evaluation of mechanical properties in both full skin and cryosection from explants. So now let's see how to apply this kind of process to evaluate the effects of blue light exposure in skin. So besides the damages induced by blue light on eye, it has been published that blue light can also induce damages on skin by reducing the synthesis of both collagen and elastin. And collagen and elastin are respectively responsible for skin resistance and skin elasticity. So we wondered if daily exposure of skin to blue light can modify mechanical properties in full skin. So at BioMeca, our setup is as follows. We have a blue light box allowing to generate blue light exposure on sample, and we have an AFM coupled with an upright epifluorescence microscope in order to do some correlation with fluorescent area or fluorescent structure with the AFM measurement. Fibroblasts are cells present in the dermis and are responsible for the production of both collagen and elastin fibers. To determine if blue light could affect mechanical properties of isolated fibroblasts in vitro, we applied increased irradiation dose of blue light on in vitro fibroblasts, and we performed some AFM measurement to evaluate stiffness after exposure. And as you can see on this graph, the stiffness of fibroblasts gradually increases with increased irradiation dose of blue light. So blue light exposure acts on mechanical properties on isolated fibroblasts in vitro by gradually inducing an increase in cell stiffness in culture cells. Then we looked at the effects of blue light directly on a collagen 1 network polymerized under blue light exposure. And as you can see, after exposure, the network of collagen 1 looks different, and it is, since you can see that collagen fibers are thinner after blue light exposure, and this change in morphology is associated with a change in mechanical properties, since collagen fibers are stiffer after blue light exposure compared to the control. So blue light irradiation has also an impact, an action on the modification of the morphology and mechanical properties in vitro on collagen 1 fiber. To go further, we analyze the effects of blue light exposure directly on full skin explant. So we perform AFM measurement directly in surface of the explant by indenting enough to be sure to measure the effects of blue light exposure in epidermis and in the dermis. And we perform force volume measurement, and we generate stiffness tomography that correspond to a 3D reconstruction of AFM measurements in which each pixel corresponds to AFM measurements on the sample. And here we have measured the stiffness. So as you can see, the pattern of skin stiffness is different before and after blue light exposure. And this is confirmed by the quantification of the stiffness, since we can see that the stiffness of the epidermis is higher after blue light exposure. And the same effect is observed on the dermis, where the stiffness of the dermis is increased after blue light exposure. Thus, blue light exposure modifies mechanical properties on overall skin structure, affecting both epidermis and dermis. So after this overview of the impact of blue light in full skin, we decided to investigate more precisely the different compartments in order to have better understanding on what is the cause of this increase in skin stiffness. So to do so, we worked on screen cryosection that comes from the explant where we have performed the 3D stiffness tomography, and we made different local measurements by AFM to evaluate the elastic modulus on two parts on the dermis. The upper part of the dermis corresponding to the papillary dermis, and the lower part of the dermis, which corresponds to the reticular dermis. And so, as you can see on this graph, we found that the stiffness of the dermis is only disrupted in the papillary dermis, where the stiffness is higher compared to the control after blue light exposure, but we have no effect on the reticular dermis after blue light exposure. So we found that blue light exposure affects only in surface of the dermis and not deeper in the reticular dermis. At last, we have checked the collagen aspect in the papillary dermis and found that collagen fibers are thinner after blue light exposure compared to the control. And this is represented on this graph, where you can see that we have a decrease in the thickness of the collagen fibers. So taken together, these results indicate that blue light irradiation significantly impacts on mechanical and morphological properties on whole skin by increasing stiffness and decreasing collagen fiber thickness. To conclude, today I showed you that atomic force microscopy is a powerful tool to study both morphology and mechanical properties at the nanoscopic scale of biological sample. I also showed you that blue light exposure has an impact on in whole skin by increasing stiffness by modulating collagen network production and structure. And from this kind of AFM measurement, we are able to extract some data such as the stiffness tomography, the mechanical properties in full skin, and morphometric parameters and mechanical properties of collagen network and fibers and elastin fibers. I hope that I convinced you that this method is ideal to study a qualitative and quantitative effect of a protective ingredient against digital pollution. Thank you for your attention. I'm checking if we have any question. I don't see. So we will be pleased to see you for the next seminar of BioMeca. So stay tuned and goodbye. Have a good day.